Yeah, thank you very much. Thank you very much for the kind invitation and welcome. So yes, I'll be talking about justified epistemic exclusions in maths today. So what are epistemic exclusions? Well, I understand epistemology quite broadly, right? So epistemology has to do with knowledge, everything to do with knowledge. So what is knowledge? How do we produce knowledge? How do we maintain knowledge? How do you transmit knowledge? How do we store knowledge? All of this has to do with epistemology has to do with all of these things. So it becomes quite clear that all of these are epistemically relevant activities for mathematicians, such as applying for funding, judging who gets published and who doesn't, and so on and so forth, right? I put academic research mathematicians here in brackets because for the purpose of this talk, by mathematician I mean an academic research mathematician, right? So the math education community, for example, sometimes speaks of mathematicians as learners, so thinking students or pupils in school. So I'll be talking about academic research mathematicians. And looking at these sorts of activities, right, so who is allowed to speak at conferences and so on, it becomes pretty clear how epistemic exclusions might go. So here's a definition taken from Dodson. What an epistemic exclusion is, namely the infringement on an epistemic agency of knowers that reduces their ability to participate. So epistemic exclusions are not a yes or no matters of affair, but rather it's a graduation, right? So any kind of infringement, anything that hinders somebody to participate in these activities would suffer some form of epistemic exclusion in some way or another. Right, so the obvious candidates for this to look for is things like race or so color of skin or gender, and there is some material on this that shows that this actually does matter. I'll mention a paper later on where we engage with that a little bit. But so what I'm interested in is this kind of overlap between the epistemological activities of mathematicians, right? So these kind of what you might call the social aspects of maths. And the ethics of this, right? So I'm interested in this intersection of ethics and epistemology of maths. So here's a quick example on how this might go, right? So the epistemic ideal, of course, is that, as long as your mathematical result is correct and somehow significant and relevant enough, then surely you'll get to you get the credits that are your due. Here's a case, just a quick one, that Hansika and I discussed in that paper over there, where we also engage with this race and gender question a little bit, on who gets to point out mistakes. So this is from an interview study with an anonymous respondent, so I won't be able to say a whole lot about this case to keep the anonymity of the respondent. But so the respondent at the time was a PhD student, right? And they were working on these two sorts of actions on some algebraic structures. And these two actions coincide if you're considering finite structures, but they do not necessarily coincide for infinite structures, right? And what the PhD student realized was that there are some mistakes in the fundamental papers on these actions, right? Namely, in these fundamental papers, one action was considered whilst features of the other ones were exploited in infinite cases, right? Where we're looking at infinite structures. So that would actually need proof, right? And they just weren't there. So the PhD student then went ahead and managed to fix it, right? So it turned out that ultimately the results were correct. It's just that the proofs had these flaws in them, and the PhD student managed to correct them. So we're talking fundamental papers of a specific field here. We discover, or a PhD student discovers some mistakes in them, manages to fix them, and then what happens is that the PhD supervisors discourage the PhD student from making these insights publicly known. Right? So what this is indicative of is that just because you have some piece of correct maths that might even be relevant, right? Remember, it's fundamental papers after all. It's not necessarily enough to get the kind of academic credit, in this case, a publication for a PhD student, out of this. Okay, So these are kind of epistemic exclusions, and what I've been doing here now is what we often do when we think ethics, right? We focus on these things where things go wrong, right? So we say, well, there's some ethical conundrum here, and this does not align with the epistemic ideal of course, you know, we have some new piece of knowledge, of course it should be shared as widely as possible, and now we run into these ethical problems, so right, somehow there is some injustice going on, right? And the epistemic injustice terminology is in fact quite big. So yeah, this is what we get here, but what I want to talk about today is justified exclusions, right? So I want to move away from the kind of unjust, right, this focus that we so often do when we think ethics, of focusing on the things that somehow go wrong, but focus on what can be justified, right? So that's what I want to talk to you about today. So here's the overview. I've already blasted through the introduction. Right, so now you have an idea of what I mean by epistemic exclusions, right? Excluding, so this infringement on the ability of somebody to participate in relevant epistemic activities. And now I want to say a little bit more about justified epistemic exclusions. And the classical case is, of course, the so-called crank, right? Obviously, the crank, the crackpot, right? These are we are surely justified, right? The mathematical community is surely justified in not engaging with their work to any degree, right? So I'll say a little bit more about these cranks and crackpots. And I'll talk a little bit about reviewing practices to make visible just how important time management and the attention economy is in mathematics, academic research in general, of course. And then I say a little bit more about how cranks are actually spotted in practice, right? So how this goes, and then I'll draw a couple of conclusions out of this, well, 3 conclusions actually. So let me start with how we think about cranks and crackpots, and I put them in inverted commas here because I have some misgivings about those terms. I do not actually like the crank terminology, and why will be part of, well, the explanation for this will be part of this talk. Okay, so here's De Morgan from the famous De Morgan laws, telling us what he thinks a crack or a crackpot, or in this case, a pseudomath is. So the pseudomath, I can't read there, I have to read here. The pseudomath is a person who handles mathematics as the monkey handled the razor. The creature tried to shave himself as he had seen his master do, but not having any notion of the angle at which the razor was to be held, he cut his own throat. He never tried again, poor animal, but the pseudomath keeps to his work, proclaims himself clean-shaved, and all the rest of the world hairy, right? The crank, right? The cranks get it wrong, and they stubbornly say, no, I'm actually right, and everybody else is wrong, right? That is the image of the crank. We get this very nice quote from A Budget of Paradoxes, so a book that a mathematician wrote on cranks. And in fact, the crank phenomenon is quite widely known in the mathematical community. I mean, most expert mathematicians have had some connection, some interactions with cranks. They write, or some mathematicians have written books about this. Mathematicians have written papers about this. Told the stories of how they engaged or did not engage with cranks, or so-called crank. There are blog posts and forums discussions, and there's a whole bunch of literature right, on so-called cranks, crackpots, circle squarers, cube doublers, angle trisectors, pseudo-mathematicians. Right? Obviously, as you all know, right, the circle cannot be squared, the cube cannot be doubled, and the angles cannot be trisected. Okay, so we've already seen that De Morgan considers them to be stubborn, right? Hodges tells us that these cranks are hopeless and mad, right? The crank phenomenon has even made it into a New York Times article where we have the rather poetic phrasing of the strange fairy dusting of lunacy, which is ascribed to so-called cranks by the author Johnson. And just like this animation, Danzig thinks cranks are a nuisance. Right, so reading through all this material on what a crank might be, what the mathematical community thinks about cranks, before I go there, I should say, of course, that this is the contemporary classic on cranks, right? This is a book that, so from this literature, I get these kind of 9 character traits of what the mathematical community thinks a crank might be. Actually, it's only 8. The first one is never really discussed, but it focuses this talk a little bit. So the first one is, of course, outsiders communicating ideas to the mathematical community. So sometimes the mathematical community uses the term crank to refer to one of its own members, such as the El-Nashi self-citation case, where that you find online that people called this person a crank because of some behavior, even though this person was a research mathematician. This is not what I want to be talking about today. What I'm talking about today are outsiders, so these are lay people. Interestingly enough, most of the ones that I've encountered seem to be retired engineers. But of course, this is I have no proper empirical evidence to back this up. This is just my experience by going through some stuff. Okay, but so they communicate their ideas to the mathematical community, and then they fail to meet accepted standards of mathematical reasoning. Right, their stuff is wrong. Right, they get stuff wrong, and they're stubborn about it. Right, they like in the De Morgan quote. Right, they maintain that no, they didn't get it wrong. They got it right. They make some absurd claims. Absurd is the politically correct term that my reviewer wanted, and probably correctly so. Hodges still calls them mad, which we don't really say anymore these days, and I also avoided the strange fairy dusting of lunacy, even though I like it a lot. It's a bit too poetic. Right, and then there are some other kind of markers that kind of mark you also as a crank, such as engaging with impossible problems, right? So trying to square the circle, or disproving intuitive results. I mean, Gödel and Cantor are the big ones that I've received. Hodges wrote an entire paper on people trying to disprove Cantor's results. And then there are big open problems, right? So Fermat's theorem used to attract a lot of attention from so-called cranks. This is now perhaps shifting, but where this will shift to is still up for grabs. Right, cranks use non-standard formalisms. Right, they invent their own notation, and this can be quite heavy notation and difficult to digest. Right, it takes a lot of time, and time will be one of the themes of this talk. It takes a lot of time to read this stuff. They use non-standard typesetting, for example. They write mathematical papers in Word. They don't use LaTeX. Right? They do not embed themselves in literature. Right? There's little engagement with what has been done before. There's no situating the work of this is relevant because it just kind of falls from the sky. There's some partial communication of arguments, right? Mostly for fear of ideas that might be stolen. Okay, so and I put 3 in boldface here. Right, 2, 3, and 4, because they are really the prime character traits of the crank. Right, the crank gets it wrong, stubbornly maintains that what they do is correct nonetheless, and they make some absurd claims in the entire process. So let's go through a couple of examples on this. So here's the classical case, perhaps, about a stubborn mathematician or a non-mathematician, James Smith. James Smith was a merchant, and he claimed that he had a proof for squaring the circle. And he went to these gatherings of mathematicians and had little pamphlets prepared and tried to engage mathematicians and talk to them about his great result. And some mathematicians even engaged with him and said, well, no, you're wrong here. And the others said, no, you're also wrong there. And there's all these little problems, right? So the expert community was quite consistent and still is, right? In what James Smith did is just wrong, right? It doesn't work. But rather than accepting all of this, he decided to publish his book, which opens as follows, right? So the quadrature of the circle, so squaring the circle, is a problem which has long been pronounced an impossibility to solve on the authority of names of such high standing in the scientific world, both in ancient and modern times, that latterly every man who has entertained the idea of attempting its solution has been regarded as a wild enthusiast. And yet the solution to the problem is extremely simple after all. And so he goes on and writes a book about his simple solution, in which he then mentions the mathematicians that he has spoken to. So he tells us in the book, look, I have spoken to the experts. All the experts disagree, but all the experts are wrong. Right? So he truly is stubborn. Interesting point of note, which I'll come back to in just a couple of slides, is that the actual formal impossibility of the result is due to Lindemann, which is only a couple of years after James Smith had worked on that. Okay, let's move to absurdity. So this is a letter from Cancioli to Davenport. Harold Davenport was the president of the London Mathematical Society at the time, and he received quite a few letters from people that he called cranked, and he collected them. There's now a so-called crank file, the Davenport crank file, which you can have a look at in Cambridge. And, well, a colleague of mine, Michael Brownie, and I did. And part of this crank file, this Davenport crank file, is a letter by Cancioli, which was received in '58. It's a handwritten letter, and Cancioli is soliciting for an academic position. And in this letter, there's a lot of text with a couple of infinite sums, which the author calls symphonies. These infinite sums are just kind of sprinkled in there. There's not much connection to the text. It's not explained why these infinite sums are relevant in any way. There are no proofs given. And then he goes on to claim that his mathematical studies are, and I quote, very related with another important problem I study now: what is the reason for all the cases of homosexuality? Without giving us any indication of how his symphonies connect to homosexuality. And he continues to tell us that one of his symphonies gave him the simplest solution for the problem of the Jews, which, according to him, is the relocation of Israel to Taiwan. So obviously this is all very absurd, right? And classifies as very, very cranky, at least in Davenport's book. Okay, so let's have a look at, right, so here we had kind of character traits, right, absurdity and stubbornness. Let's have a look at the kind of features of the work, right, the problems engaged with. I thought one of the examples I'm going to give is the impossible problem by the Académie Royale, the French Académie Royale. Here's the text in English because I would just butcher it in French, so my apologies for this. I take the translation from Danzig. The important bit is that the Academy has resolved this year not to examine in the future any solution to the problems of doubling the cube, trisecting of the angle, and squaring the circle. And then it continues, right, because the long experience has convinced the Academy of the little value that would accrue to science were the examinations of these pretended solutions to be continued. Right? So what the Academy is telling us is, look, we have years of experience of people submitting kind of solutions to these problems. These problems just cannot be solved, especially not by outsiders, so we're just not going to look at them. Right? We don't want to spend time and our attention on this. We are not going to look at them just because of the kind of problems they're engaging with, right? Because, well, they're impossible problems to solve. Of course, remember that the actual formal proof that these problems were actually impossible to solve came about half a century later by Wanzel, and then what I mentioned already, the Lindemann proof. So when the Academy wrote this, they didn't actually know it's formally impossible to prove any of these results. Nonetheless, they said, well, you know, this is just taking up too much time with way too little benefit for us, so we're not going to look at this anymore. Okay, so that's the impossible problems bit. And then there are big open problems that so-called cranks like to engage with. So here is the Royan case, right? So Thomas Royan has mathematical training and then worked in the industry for a while. When he was retired, he turned his attention to the Gauss correlation inequality, which was an open problem for over half a century. And he found a very, very elegant and easy proof. I haven't looked at this proof ever, so I'm reliant on what Quantum Magazine has to say about the simplicity of this. But okay, so in there we read that, you know, first semester students could digest the proof. Right? It's quite a simple proof. Right? And now he writes this all up, but he writes this all up, but he uses Word for this rather than LaTeX, right? And he doesn't do the kind of standard means of communication for communicating the results. So he doesn't go to conference to speak about it. He doesn't upload his paper to the archive. Right? It's not announced in any kind of classical way. He just has this new result, and then he tries to push it onto some mathematicians to have a look at. But these mathematicians look at this and see this. It's a big open problem. It's a layperson who uses very elementary methods to solve this problem, and it's all written up in Word. It just looks cranky, right? You look at this and you think, that's right. Most likely it's going to be wrong. It might be right, but most likely it's going to be wrong. So the mathematicians decided, most of the mathematicians that he sent it to decided, well, I'm not going to engage with this. I'm going to give you a quotation of this later. So what happened was that ultimately, because Royan still had a friend who was working in academic mathematics, who helped him to typeset it all in LaTeX, communicate in the kind of right sort of ways, use correct channels. Ultimately, the mathematical community became aware of this result, and it's now celebrated. But as Quante so aptly titles the piece, right, a long sought proof, right, over half a century we were looking for this, found by Royan, but then almost lost, right? Basically, nobody paid attention to this at first, right? He was kind of lucky that somebody paid attention to it, because ultimately there was epistemic merit to this, even though at first it just didn't look like it. So the takeaway from all of this is that the time management, right? So looking at things and saying, well, does this look like something that might have some kind of epistemic benefit? Right? That's a fallible strategy. Right? Scanning for these what I call markers of competence, right, is a fallible strategy. But I will argue that nonetheless it's justified. Right? It's a justified strategy. And why is it justified? Because we will need to manage time. Right? Mathematicians, like all other academics, need to manage time. In fact, that's nothing particularly special about the crank case. And my next slide will talk about this, because this happens a lot in reviewing practices as well. Right? So this B section of the talk is now is meant to show, well, time management is it's a fundamental aspect of ordinary academic research. I'll talk a little bit about how this goes in maths, and then I'll circle back to the crank case and have a look at how cranks are actually spotted, right? So what are the strategies used to spot cranky work, right? To say a little bit more about that, what I just hinted at in the Royan case. Okay, so let's start with the downer. Here's Nathanson telling us that I think most papers in most refereed journals are not refereed. There's a presumptive referee who looks at the paper, reads the introduction and the statement of the result, glances at the proofs, and if everything seems okay, recommends publications. Some referees check proofs line by line, but many do not. Right? Now, this is a mathematician telling us some personal experiences and opinions. By now, we have a body of literature on the literature on proof validation and peer review, which comes from the sociology of knowledge, if you will, some philosophy of maths. So people have been looking at how does peer review go in maths. And what tends to happen first is that a submission comes to the editor, and the editor then sends it out to an expert in the field for a quick opinion. I call it a 5-minute judgment here. It doesn't necessarily have to be 5 minutes, of course. But okay, so and this expert will then quickly judge whether the submission is in scope, right? So if this is an algebra journal, but some probability theory proof is submitted, well, maybe that's a good reason to reject it, regardless of the correctness and significance of the work otherwise. And is it generally valuable, right? A proof that, I don't know, 5 plus 2 is 7, it might not be as exciting, even though it is correct. But so in this quick opinion, there's no checking for correctness yet. Once a quick opinion has passed, once the person says, yeah, okay, this is suitable also for this type of journal in question and so on, then it goes to a reviewer. And the epistemic ideal, of course, is that the reviewer now does some line-by-line checking, right? So the idea is that a reviewer with due diligence sits down and reads the proof and digests every step, right? Does it, right? Are these good assumptions, right? Are the conclusions valid, right? Do the steps work? Is this a good argument? Is this a good mathematical argument, right? And the truth of the matter is that line-by-line checking is hardly ever done for a paper in its entirety, right? Most of the time, reviewers check some bits line by line, and employ a host of other strategies otherwise. And these strategies include comparison, right? So compare the proof to something else that you might know. Deference to authority, where you think, well, okay, so I know who the author of the paper is, and this person is very, very smart, so this proof will probably be correct as well. Right? There is some inconsistency with literature, right? Does that hold up? Example-based reasoning, right? 3 is prime, 5 is prime, 7 is prime, let's check another one, 13. Well, okay, maybe the claim of the paper that, all odd numbers are prime is actually correct. Example-based reasoning, obviously fallible, right? As all these strategies are, they're all fallible strategies. Non-validation is a nice one, where the proof is not checked because the validator regards himself as not expert enough to digest the proof. Or deflection is perhaps my favorite. The proof is not checked on grounds that the authors wish to see the proof published, so they need to ensure correctness, right? So it's the author's job to ensure correctness. All of these have been reported in interview studies and the like by mathematicians that actually do some reviewing. And obviously, what all these strategies do is they allow you to skip elements of the proof, right? You don't read every single line by line, because sometimes you can just look at things and say, yeah, okay, that looks enough like something that I know, that will work, or yeah, I kind of believe this, right? This is okay, and here I have my doubts, so I might be doing some checking again, and then these other bits I'm gonna, skip again. Why? Well, because it saves time, right? To digest a full-blown proof in detail, everybody who has done some maths knows that this can take an awful amount of time. And to save some time, these reviewing strategies are routinely employed. Sometimes with feelings of guilt, with the idea that we shouldn't be doing this. Remember Nathanson, who lamented this. So this is done. So the takeaway of this section is that time management is just a very ordinary feature of academic research, right? Also of mathematical research, of course. Mathematicians routinely employ the kind of fallible strategies, right? Like example-based reasoning, when engaging with mathematical works, right? When reading mathematical works, when trying to judge whether it should be published or not, these kind of fallible strategies are used, right? Okay, so time management is somehow relevant, right? And then surely this is also relevant for our case today, for the kind of cranks, right? That we shouldn't be engaging with stuff where the likely outcome that this has kind of any epistemic benefit to us, if the probability of that is so very, very low, right? Then you might not want to spend hours and even days on engaging with this, right? So let's have a look at how the mathematical community judges kind of crankiness, right? So how are cranks spotted, right? Spotting mathematical crankery is... and there are numerous kind of partially humorous lists online on how to do this. So here's a little bit of Chris Caldwell, who has this kind of crackpot index, as he calls it. And he distinguishes these kind of 5 categories. So one is syntax, the other is subject and claims, hubris, process and proof, and whining. And he gives out, he has all these kind of statements in there which all give you penalty points, right? And if you have too many penalty points, you're probably a crank. I would like to split it up slightly differently. I want to be looking at behavior of a person and features of the work. So here are some examples of behavior of a person, just taken from the website here. So you get 10 penalty points for expressing that expressing fear that your ideas will be stolen, and a whole 50 penalty points for failing to respond to appropriate corrections, questions, and challenges. Right? The features of the work, you get 10 points for each new term you invent without properly defining it, and another 10 for citing an impressive sounding but irrelevant result. And the list contains like 50 bullet points or something. I don't know. It's quite long. But in general, this can I point? No. The behavior of a person gets more penalty points on average than features of the work. And that really matches nicely with this kind of community conception of cranks that we've seen before. And because what really matters, right, are the kind of absurdity and stubbornness features, right? That's what we think about when we think about the crank, right? That's what De Morgan was stressing when he was talking about the monkey, right? The kind of behavioral traits of this outsider. Right? And so this is what in this in the crackpot index gets the most point. If you display this kind of these kind of behavioral features, then you get the most points, right? But what is done for kind of spotting mathematical crankery is looking at features of the work, right? Remember the Royan case? It's written in Word. It's such an easy proof for a big open problem that's not going to work, right? Those are the features of the work. There's no engagement with the actual author to find out what the author's behavioral patterns or epistemic vices really are. So here then is the case study that highlights this kind of most strikingly, I thought. Which is the archive, which is filtering solely by features of the work, right? So I suppose that you all know what the archives are, right? So it's this preprint server, right, of e-prints, they call them, where all kinds of natural sciences and but also mathematicians can upload their work prior to publication. And the archive presents itself as a curated research sharing platform open to anyone. Open to anyone in the sense that there's no paywall, right? You can have a look at everything, but it's curated in the sense that there's a moderation process that looks at the submissions that are uploaded. So how does this moderation process go? Well, first of all, the moderators are asked to check whether a submission satisfies what they call referability criterion. So would that submission be sent out by an editor of a journal for actual review, right? And if in doubt, moderators are asked to err on the side of acceptance. These archive moderators, at least for maths, are unpaid volunteers. And I mean, the archive is huge, right? Over 2 million e-prints on the archives. I checked this like a year ago last, and that was over 2 million. So by now it's even bigger. It's even more over. So what this means is we need some kind of automation for this process, right? So what has happened is there are now these kind of 3 filters. One is just for technical problems, by checking that it's not the same submission uploaded twice, or that name and email address are mangled up or something like this, right? It's just technical problems ensuring that the submission is kind of done in the proper way. And then there are these kind of subject classifier and stylistic filters. And here is Paul Ginsberg to explain what that might be. So Paul Ginsberg is the founding father of the archive, the one who started it all. And he tells us that, right, so the subject classifier, right? If you just use technical words, say superconductivity, anything that isn't on the list of top few hundred most frequent words, not surprisingly, if you look at those technical words, you can build a very good subject area classifier, because now you're just throwing out stylistic differences. You're just focusing on content. You see whether the article contains black hole, or whether it contains superconductivity, or whether it contains databases. You get a very, very accurate fine-tuned classification. So what this does is it helps the moderators to see whether the author has uploaded their paper into the right kind of category, right? So if this is a paper in number theory, then, but it's been uploaded to set theory just by human error because, on the drop-down menu you click the wrong button. It happens, right? The subject classifier is likely to spot this, right? The subject classifier, and then it spots this and flags this to the moderators, and then the moderators can have a look and then say, oh, okay, we just need to change the subject classifier of this submission. Or potentially, here's a problem. Okay, then the second one is the stylistic filters, so outliers, writing in a style which is deviating in a way, right? I find this by doing a principal component analysis and dimensional reduction. I do not actually know what this is. This is some serious data science, but I trust Ginsberg when he tells us that you do this and you find here are the physics articles, here are the computer science articles. You can see differences within, and then you find these outliers. So, right? So you have in a community, there's a certain way of writing, at least according to Ginsberg, right? A certain stylistic way where, in physics or particle physics might be writing differently than probability theorists, right? The style of writing a paper is just different, right? And these stylistic filters are supposed to catch this, right? And the big reveal comes now when he says, we've actually had so you have these 3 filters, right? And we've actually had submissions to archive that are not spotted by the moderators, but are spotted by the automated program. All I was trying to do is build a simple text classifier, and inadvertently, I built what I call the holy grail of crackpot filtering. Right? So here Ginsberg tells us, look, we can just run our computer program, right? These 3 different types of filters, and if they all flare up and say, this looks weird, right? Because it uses certain words it uses words from way too many different fields, right? Number theory papers are not written like this, even though it should be a number theory paper. It just looks weird. Also, it doesn't use the kind of way of talking that usually is employed by number theory. Then this flares up, and what Ginsberg is claiming here is that usually what you get out of this is that this is a non-mathematician who has tried to submit something to the archive. Remember, it's kind of more or less open to anyone. More or less because it's a bit more complicated, but let's not get into this now. So you can automate kind of filtering out of, these submissions do not have the kind of markers of competence that would warrant further engagement, right? So that works of cranks. But of course, what this is doing, right, what this computer program is doing is not engaging with the behavior of the authors of these works. It's not meant to do this, right? All it does is checks for features of the work, right? It is just checking for what Cardwell gave out the least points, right? It's not checking for stubbornness of the authors, right? They might have just made a simple mistake and would even agree that they made a mistake if you were to talk to them about it. But this is not what the program does, of course. It's not checking for absurdity in any way, right? It just uses markers of competence, right, features of the work, and judges by these features, does this look cranky or not? Right? So that's how our cranks are spotted, right? This saves some time, of course, right? So now you can just look at the way a piece of maths is written and decide, do I want to spend any kind of attention on this, right? Or is it just not worth my time? There's an important difference here between the reviewing case and the kind of spotting of mathematical crankery case. In the reviewing case, the reviewer is already committed to spend some sort of attention to the piece of mathematics under investigation, right? That's why they agreed to review the piece, so they have some obligation to spend some attention on this. So it's about the engagement. How do you manage your time when engaging with a piece of maths, right? That's what happens in the reviewing case. The crank case is a bit different, because here it's not how do you manage your time when engaging with the piece, but here it's, should I pay any attention to this at all in the first place? This is not about, should I read the proof line by line, check every single detail. This is, should I read the proof at all? Right? And the way to do this is, or the way it is done, I should say, and the way it is done is by scanning for these markers of competence, scanning for these stylistic differences, for, does it look cranky? Is it written in kind of standard formalisms? Is it embedded in the literature? Is it, what else did we have? Embedded in literature, standard formalisms, standard typesetting, right? Is it in LaTeX, and so on and so forth. Right, so that was the descriptive part of the talk. Let's get to my 3 little conclusions. So first of all, a one-sentence summary of this. So because academic work requires time management, as I've been stressing over and over again, mathematicians are justified not to pay attention and much less to engage with every mathematical argument. Right? It's just not feasible. Right? They are justified in doing this. This does mean that we are divorcing something that I just kind of rushed over in the beginning. Maybe I said, when we think ethics, we focus on, unjust exclusions, and I want to be talking about justified exclusions. Right? This divorces the kind of justice and justification idea. Right? So whether the way that outsiders are handled today by the mathematical community, right? So-called cranks are handled today. Whether this is kind of ethically just, that's a separate issue that I won't be dealing with today, and I haven't been dealing with in the paper either, at least not to any large amounts. What I'm dealing with is kind of this justification idea, right? And the claim is that, look, time management justifies to just not engage with everything because we have to manage our attention. Our attention is a limited resource, and as a limited resource, we need to manage it. Okay, so here's the first insight of this talk then, right? So there are justified epistemic exclusions in mathematics that are not based on incorrect mathematical arguments, right? So when we're thinking cranks, right, we might, and I've been arguing that, well, it's justified not to read their stuff because it looks so weird and we have to manage our time, so we're justified at not reading certain pieces of mathematics. But this is not based on them being incorrect. This is just based on them looking funny. But there's some justification to this, right? I think I have a quote here. Yes. So for Hirsch, right, this is a real dilemma, right? Hirsch tells us in this New York Times article, who is going to stroll through pages and pages of stuff that is very hard to understand when you don't have to do it. From the point of view of these guys, the outliers or cranks, we, the mathematicians, are arrogant, unwilling to reconsider ideas. And why shouldn't they expect a responsible scientist to look carefully at some new idea that might be important? Well, I've given a reason why scientists shouldn't, right? They need to manage their time. And that might be a good reason to not engage with such cranky works. Right, here's the second insight, more of a corollary from the first, really. That there are cases where mathematical community is justified in excluding authors from mathematical practices, even if the author's arguments are correct. So remember, we are talking cranks, so there is this judgment of whether or not we should be paying any kind of attention to the piece of work is before we're actually reading the work at all, right? And we might be rejecting something because it just looks so cranky, it doesn't look right, it doesn't look good enough. But nonetheless, it might be correct, right? In fact, this is what happened in the Thomas Royan case. So here we have Boris Klartag of the Weizmann Institute in Tel Aviv, who recalls receiving a batch of 3 purported proofs of that Gauss correlation inequality, including Royan's, in an email from a colleague. When he checked one of them and found a mistake, he set the others aside for lack of time. Once again, time flares up, right? So Klartag tells us, well, it looked off, so I didn't check it, right? I didn't actually pay any kind of attention to it. I had it in my inbox, and maybe later if I have more time, but I'm not going to do this now. But as we know now, the proof was indeed correct. It is a correct mathematical result, and if Klartag would have been the only one who is doing the judgment on this, this would have just been a piece of knowledge that is lost, right? This might happen in the way that cranks are currently treated, right? I still think there's some justification to this, right? Because we still need to manage the time. Well, mathematicians still need to manage time. But this is one of the upshots that comes out of this, right? There might be some great knowledge that is lost. I mean, of course, for the purposes of the paper, I would have loved to, find this one piece of hidden mathematical knowledge that, was rejected as very cranky in the way back when, but was kept on some attic somewhere, and I could now discover it and say, look, here, actually, there is something to it. But, I mean, the whole point is that you can't find them. I mean, they're hidden. They're buried in history, right? They did not make it. Those are mathematical arguments, if they exist, which maybe they don't, but the Board's case, the Royan case, sorry, at least suggests that there might be some. And there are others. I mean, Marjorie Rice and her tilings were another example of somebody whose work looked very, very cranky, right? Non-standard formalisms, non-standard means of communication, and so on. Nonetheless, it got accepted, and she's a famous amateur mathematician now. Right, okay, so that was the second insight, and here's the third insight then, that the way we think about cranks differs from the way we spot them. And to say a little bit more on what I mean by we here, let me introduce this distinction between operative and manifest concept, which goes back to Haslanger. So Haslanger tells us that the manifest concept is the more explicit, public and intuitive one. The operative concept is more implicit, hidden and yet practiced one. What does this all mean? Well, here's an example. Think of parent. Oops. So it's an example that Haslanger gives us. So the manifest concept is the concept that we have in our head, like a concept that comes to mind when we hear the word parent. And what we instantly think about is biological parent, right? That's the thing that comes to mind. Where the operative concept is the concept as we use it, right? So when a school is sending out a letter to the parents or is organizing a parent night, they do not only speak to biological parents, right? They speak to step-parents, legal guardians, grandparents, aunts, uncles, all the siblings, informal substitute parents, what have you. They're speaking to primary caregivers, right? So there is this, we use the same word parent, right? But there are these two different meanings, right? The manifest meaning is this thing that we have in our head, and the operative meaning is how we actually use it in practice, if you wish, right? And using this terminology, we can now say that the manifest crank, right? The crank as this hopelessly mad, stubborn, and absurd figure that gets stuff wrong, right? Is a very different figure from the operative crank, who is just writing in a style that doesn't have the certain markers of competence that encourage the mathematical community to engage with their work. And with that, I say thanks.